Hi everyone. Today we are talking about structural geology. Structural geology describes the architecture of the Earth's crust, how it breaks into pieces, how mountains and valleys are found next to each other. Basically, we're talking about the rocky Earth, so you can ignore the plants and the ocean, anything that isn't made out of rock. How do rocks respond to tectonic forces? This also falls under structural geology. You've already learned about plate tectonics, and today we'll talk about the forms and shapes that are created by plate tectonics. This is a picture of the geosphere. This is what the Earth would look like if I removed the water in the oceans. And this is the crust of the Earth we'll be describing. Some geologic structures include folds, joints, and faults. Probably you are familiar with the San Andreas Fault. That is a huge crack in the earth along which movement occurs. But sometimes a crack doesn't have movement, and sometimes a crack doesn't form. A rock might bend. When rock is bent, we call it a fold. And bends in layered rock are produced by plastic strain. Plastic means not brittle. If you have ever played with Play-Doh, for example, or cookie dough even, you know that you can bend it. Is it a solid? Absolutely. You can't drink cookie dough, but it doesn't break when you deform it. It bends. This is an example of plastic deformation. Synclines, anticlines, domes, and basins are types of folds we will discuss in the next slide. In a syncline, if you bend the rock, it forms a fold that looks a little bit like a smile. The middle is down and the corners are up. The youngest beds are in the middle. Smile and syncline both start with S, if that's helpful to you. In an anticline, the rock bends the other way so that the edges are depressed and the middle is pushed up. It's shaped like an arch. Arch and anticline start with the letter A. Maybe that will help you remember them. The oldest beds are exposed in the middle. This picture shows a syncline and an anticline formed together. In this example, they are both very small. That's a peso, the coin in the picture, used for scale. But folds don't have to be small. They can be the size of mountains. Big or small, they all form from the same tectonic forces. A dome is a sort of 3D fold. If you can imagine a tortoise walking around, a tortoise is shaped like a dome. All the layers dip away from the central point. This photograph shows a very famous dome in Wyoming called Sheep's Pass. I visited this place as a student and collected what's called gastroliths, little stones that dinosaurs used to swallow to help them digest food, herbivorous dinosaurs only, like Brontosaurus. And then when they died, the rocks could be found in this place. A basin is shaped more like a cereal bowl. The middle is the lowest point. Now, in this case, here is a map of the state of Michigan. The entire state is a huge basin. Sometimes a rock does not experience plastic deformation. It experiences brittle strain. Before, we used the example of cookie dough. Now imagine a very stale Chips Ahoy chocolate chip cookie. If I apply pressure to it, it won't bend, it will break. And when rock breaks, we call that brittle. In the example of a joint, the rock breaks to form cracks. Sometimes those cracks move. When they move, we don't call them joints anymore, we call them faults. Technically speaking, a fault is a fracture along which displacement occurs. In the case of the San Andreas Fault, The state of California is moving north, while mainland USA is moving south. Slowly, of course, but moving nonetheless. There are two types of faults, dip slip and strike slip, which we will talk about in the next slide. This world map, incidentally, is covered with tiny lines. Every single line is a fault. Faults are not rare on planet Earth. They are everywhere. It is a very tectonically exciting planet. And the US has a lot more to it than the San Andreas Fault. It's covered with faults. In a dip-slip fault, we have up and down motion. We call this type of motion normal or reverse. In a normal fault, one block moves down and the other block moves up. The block that moves down is on top of the inclined fault. In this image, it is on the right-hand side. It is called the hanging wall, moving down. Normal faults form when you stretch the coast or crust, whatever you're stretching, due to tension. Normal faults create a beautiful topography. Here's a normal fault. Hanging wall moved down, footwall moved up. In a reverse fault, the hanging wall moves up and the footwall moves down. This is due to compression. A beautiful reverse fault is in the Chief Mountain, which is in the United States, American West, shows the hanging wall, which has slid many hundreds of kilometers from its original location. In a strike-slip fault, we don't have up and down movement, we have side-to-side movement. The most famous example of a strike-slip fault around here is the San Andreas Fault. If, like the San Andreas Fault, one side moves to the right of the other, we call it dextral. If one side moves to the left of the other, we would call it sinistral. The image on the left shows a dextral, also called right lateral fault. The San Andreas Fault is a right lateral fault, but worldwide there are both kinds. This map of North America shows the San Andreas Fault. North America moves to the right of California. California moves to the right of North America. This road was damaged in an earthquake on the San Andreas Fault. This side moved to the right of this side. It is a right lateral fault. Faults can collect very valuable minerals. This fault surface is covered with gold. Californians are familiar with the gold rush of 1849. Most of the gold collected during that period was called lode gold, and it collected right on faults. Sometimes pieces of that gold washed downstream, where they were called placer gold. We won't cover gold in this unit. I just want you to know that faults are related to very valuable minerals. The reason we care about structural geology is we want to identify structural hazards before we build homes on them. They help us determine areas for safe construction. This home has walked right off its foundation during an earthquake. Had it been bolted to its foundation, it might have survived the earthquake. Had the homeowners known there was a fault under the house, they might not have bought that house. Sometimes we don't identify a fault until it moves, and then it's too late. Geologists map structural geology. You can see on this map little lines with teeth on them. Each one of those is a fault. Now that you know about structural geology, hopefully you will think about this when the San Andreas acts up again, as certainly it will. Have a great day.